All right, so before I start, a few little hiccups of the homework, I suppose. So the auto grader is up for the MapReduce and unsupervised learning assignments, but we're still having some trouble getting the grader working for the probabilistic modeling and the deep learning ones. Unfortunately, this is an issue with AutoLab. The version they have of Khan doesn't appear to be working with our versions of our graders. The graders all work, but they don't work on AutoLab. So we're trying to resolve it. The TAs are working as fast as they sort of can on that, but it's still not up, and I don't quite know when they're going to be up. So if it goes on much longer, we will push the deadline back a little bit. We can't push it back too much further because it's just the end of the semester. In fact, it's already due in the last day of class. So we can't do much more, but we'll try to do our best to sort of get that so that you don't hurt unduly by that. Having said all that, hopefully you can still do the assignments, right, and evaluate them compared to the results in the notebook. But we are aware that the auto grading performance is not always the same as local performance, so we want to get those up as soon as possible. It did not meet the 48 hours for just those two for this one, so that is what it is. But we'll try to get those up, and we'll notify people on Piazza when those do come up. Because that's the main thing. I think I also am trying to filter out some of the additional notes on those, just the things on those assignments, to get at least those published, and those hopefully within the next couple days now will be up. Okay, so having said that, this lecture is now a little bit of a switch from the past few lectures. So we're not going to talk here about. It's very. All right, I'll wait a second. All right, we're not going to talk too much about any more about kind of technical, algorithms, stuff like this in the next few lectures. What we are going to talk about, though, is sort of the more practical elements of debugging data science today. And then next lecture, we're going to go kind of through a walkthrough of just an example data science problem, like you might do on the project. But of course, we're doing it in the span of a single class, so it's going to be a little shorter than a whole project, of course. All right, so this lecture is about debugging data science. It's actually one of my favorite lectures to give in this course because debugging data science, for whatever reason, seems to be at the actual heart of what people do when they do real data science or data science work, but it's very rarely covered in most lectures. So most courses spend a lot of time covering the algorithms and the techniques that you would use when you apply data science, and that's what we've done largely so far in this class. But when you actually sit down to apply these techniques to a new problem you haven't seen before, chances are things are going to come up that you don't expect. And so what this lecture is about how you deal with these problems in data science when they do come up. And what we'll do is we'll sort of talk about the nature of data science debugging versus normal debugging. And then I'll kind of give you the sort of lessons I've learned and the procedure I follow when tackling a new data science problem, how I kind of go by it step by step, and to hopefully ensure that at the end we have a successful result, right? You can't always guarantee success. There are impossible problems, both in quotes impossible and genuinely impossible problems. But at least this procedure is, in my experience, led to typically successful applications of a lot of these techniques. So I want to start off with, though, talking about what makes data science debugging so hard. So imagine this scenario, right? I know it's hard to imagine, but just imagine it for a second. And the scenario is you have some task you're given as a data scientist, right? You take this course, you apply to a data science position, you get your data science position after graduation, and then all of a sudden you're given a new task. And so you go about trying to attack it the way you would a data science task, right? You formulate, and I'll even consider like a supervised learning problem here, right? So, you define some input-output pairs you want to solve with some machine learning algorithm. You run the machine learning algorithm on that task, and when it comes out, what happens is it just doesn't work, right? So your performance on some held-out set is no better than random chance. So the first thing to keep in mind is that this happens to everyone, right? This is the default behavior. When you address a new domain, it's not the exception to the rule, it is the rule. This will always happen when you're sort of looking at a new task, a new application area you haven't thought about before. But the saying that I like is that what differentiates experts in data science from novices is not the first thing you try, because everyone tries the first thing. It's the second thing you try when that first thing doesn't work. It's hard to get anything named after yourself these days, so I'm going to call this, I'm going to name it after myself and hope this sticks. I can do it in my course, so maybe I'll now indoctrinate everyone. But what's happening here? And what's happening here, I like to contrast with normal debugging. So you've all programmed before, and you know how to kind of debug normal code, right? The way you debug normal code is you kind of have, so you have some input-output pairs that you want to produce from your code, right? I have a list. I want to produce a sorted output of, a sorted list with all those same elements, right? I want to sort the list. And then you have a mental model of how that algorithm should kind of work, right? You sort of think, okay, I have some preconditions and postconditions about what should happen after each step in the algorithm. And so what you do is you trace through the execution of the program, right, line by line, either with a real debugger or with print statements, if you're a real data scientist, because we don't really code very well. You trace through it line by line, and you see where the state of the program diverges from your own mental state, right? And when it does, you found the bug in the program. Or when it doesn't, you found some error in your mental model of the algorithm, right? If everything is correct and isn't producing the right output, you found sort of an error in your mental model. But something is very different about data science debugging. Because in data science, right, we have input-output pairs. But we have no real mental model of how this mapping should work. In fact, that was the whole point of these automated data analysis techniques, these machine learning techniques, is that the algorithm should figure out what the mapping from inputs to outputs is, right? What the predictions should be. And so what can you do to sort of say why this is not working, right? It seems very much harder to do this because you can trace through the algorithm, right? You could do that, but it's not really the problem, right? Doesn't matter if your logistic regression routine is correct. That's not the problem. The problem is that somehow, when you run that routine on the data, it's not giving you the desired result. It's not actually producing a valid mapping from input to output pairs, from inputs to outputs rather. And so this sort of really fundamentally differs from normal debugging in this way. Now, the question is, what do you do when, therefore, your program is not, your machine learning model is not working as expected? Now, I should say that many of the topics here that I'm going to cover about how you do that, and I'm going to take you through kind of my process to how I figure out what to do when the algorithms are not working the way I want, which, no matter how much experience you have, as I said, that is always the default behavior anytime you apply an algorithm to a new task. So I should emphasize that many of the topics here in this lecture kind of overlap with the sort of a general topic on debugging machine learning, right? So debugging machine learning, there actually are other lectures on this that I've seen that are quite good. I think I have some pointers to those in the notes online. But I think that debugging data science is a little bit broader a term, right? Because debugging machine learning typically assumes that your problem that you're fitting to machine learning algorithms actually is possible to solve, right? Can be solved by a machine learning algorithm, and you just need to sort of tune it, maybe add features, maybe choose a different algorithm, maybe tune it differently in order to see, maybe get more data. But the assumption somehow is that the problem actually is possible. But with data science, I think it's more often a notion of debugging the problem rather than debugging the solution method, right? So what typically happens, the typical reason why data science problem is not amenable to sort of algorithmic work is that the problem itself is somehow malformed, or there isn't enough information in the data to actually predict what you want to predict. Okay? And so that's actually going to be the majority of what I focus on in this lecture. It's actually not about debugging the algorithms, but about debugging the problem itself. Because the problems you create are really what makes something possible or not in the realm of data science. Okay, so I am going to use a running example here, not so much in the slides. And the slides are more just notes to help me remind me what to talk about for this one lecture, to be honest. But I want to use one example that kind of I've actually worked on in industry before. And it's one that I actually think is a good kind of illustration of the types of problems you might encounter. I mean, one of many, of course, but it's a nice illustration. And this problem is one called predictive maintenance. So the idea here is that you are running or somehow operating a large factory, or working for someone that operates a large factory, and you want to predict which machines in that factory are going to fail. Okay, so you want to maintenance when the machine goes down is expensive, right? You lose production, all that kind of stuff. So you want to know ahead of time what's going to fail, so that you can fix it ahead of time and prevent them from going down in the first place. So it's sort of a very common task. Really, actually, a large portion of data science is devoted to this exact problem, or at least a large portion of applied industrial data science looks at this kind of exact problem. Trying to figure out, diagnose problems in machinery or other equipment before they actually cause real problems. And so the input to the system is, a bunch of sensors, say, recording the state of the system, right? So maybe we have, a vibration sensor, a noise sensor, things like this, and they're monitoring the machine as they go along. And then on this day, this is the present time, I want to predict, will the system fail, say, in the next 90 days or something like that, right? So it's going to fail in 90 days, yes or no. And I guess that window is arbitrary. I could pick, 30 days, 60 days, whatever. But is it going to fail in 90 days or not? And now this is a problem where we have sort of historical data, right? You can look in the past, look at signals in the past, look at the times in the past and say if they're going to fail or not in 90 days. It's a pretty nice supervised learning algorithm. But when you actually apply this machine learning and other analysis techniques and practice to this, you find that a lot of things can go wrong very easily. And so this is going to be, at least if not in the slides itself, at least when I sort of maybe try to make this a little bit more concrete, I'll come back to this example and offer some illustrations about what things you do when this particular problem doesn't come up or doesn't seem very amenable to some of the techniques we talked about so far. Okay, the other thing I should say is this is a little bit more of a, feel free to interrupt at any point and ask questions. It's a little bit more of an interactive lecture than the other ones, or could be at least, depending on how much people want to ask. So feel free to just interrupt and ask questions at any time. It's a little bit more high level than the other lectures we've had so far in this class. Okay, so let's say you have this problem now, and I want to go about solving it with a machine learning algorithm, right? Okay, so the step one of data science is to determine if your problem is impossible or not. This is a surprisingly large number of times you will find out your problem actually is impossible, or at least is not really amenable to the techniques to any kind of easy analysis. And it's good to know that sooner rather than later, right? So step one, determine if your problem is impossible. And the reason is that there are plenty of tasks that would be really nice to be able to predict, but there's just no meaningful way to actually be able to do it. So several people for their projects, for example, propose predicting stock market effects from Twitter. And I will say that this is not a possible thing to do. I mean, maybe there is some signal for people that know this really, really well. But if you try to do this for a class project, you'll either just fit to some noise and not succeed, or more likely you will just have some random answers that clearly aren't actually showing anything meaningful or not. So we'd love to predict this thing, right? I can go in the past. I can create a data set that says, here's what people are talking about on Twitter. Here's the stock market the next day. Try to predict what's going to happen to it. But the reality is there's no actual signal in that data to actually make your predictions. Certainly none that you can actually still extract, from any reasonable way. If there ever was one, I'm sure it's already been taken out by people that are doing this in a very sophisticated manner. The problem here, though, is that, we're still optimists fundamentally, right? And so we really want to predict things like this. And it's very hard to prove a negative, right? It's hard for me. I mean, I can say confidently that this one is impossible. The papers that have claimed this have all been pretty thoroughly debunked. But it still seems possible, right? There's maybe one special Twitter account you could follow. This one person knows exactly what's going to happen in the stock market tomorrow. And so if you just found that person and added that feature to your data, you'd be able to do this, right? And that hope always sort of is possible, right? This is always possible that one more feature or one more data source could just make your problem addressable. And so how do you go about proving to yourself at least that your problem actually is impossible, or is it just a matter of working harder, right? Is that the real issue here? So the way to go about this is to not think so much about whether your problem is impossible, right? Because that's a very hard thing to prove. But rather, as a surrogate for this, ask yourself if you can solve the problem. And to do that manually, I mean, right? And I mean this actually quite literally. Okay, so I mean, if you want to solve a prediction task with some machine learning algorithm, you first create a little interface where you can play a game and solve that task yourself. Okay, so if I want to classify signals of past time to whether or not the device is going to fail in my factory, I actually plot those. I graph those signals. I look at the current time. I can't peek ahead and cheat, right? Because if you can peek ahead and cheat, you can always backfit things and say, oh, well, that failed because these things were like this. But no, you can't cheat. You have to actually give yourself the same data the algorithm has, and look and say, given just this data, would I predict if it fails or not? And you actually score yourself, right? So you actually keep track of how you're doing and score yourself and see if you can actually predict whether or not this device is going to fail. Now, this is actually confusing to a lot of people because in some sense, the whole idea of machine learning is that it could incorporate more than we ever could ourselves, right? It can use higher dimensional data, more sources of data, it can do it all in a much, much better fashion. So how on earth could we actually do that, right? And so I think that the idea here is, what about these superhuman machine learning, right? We were taught that machine learning could do these things that we can never do ourselves. So how is this possible that we are a good surrogate for whether a learning algorithm can do it or not? But this is actually, for the most part, just not really true. It can be, but it's not in most data science tasks. All right, so in most data science problems, the advantage of machine learning does not come from superhuman performance. It comes from the ability to scale these things to a much greater and faster degree than you could ever do kind of with scaling experts, right? So it's actually quite hard to outperform experts, domain experts at a task like this, right? So it's hard to outperform people like, the maintenance people that actually maintain factories. You may eventually, and in fact, some of the goals is that through this you will eventually do that. But the real advantage of machine learning is not in being able to outperform people. It's being able to sort of automate these tasks in a way that can scale essentially infinitely, right? So that I don't need to pay someone to look at every single signal of on my sensing on my machines, pay them to analyze what's going on right now, every day, and by the way, every day doing it again, right? Because every day they have another set of signals to look at and say which one's going to fail, right? So the advantage of machine learning is not in the ability to sort of outperform humans. It's very much in the ability to sort of match human performance, ideally match it, maybe exceed it, but do it in a very scalable manner. And the lesson here is that if you can't make good predictions, for the most part, neither will a machine learning algorithm, right? Neither will any kind of analysis technique you can really apply. And the reason for that, again, it's not that it's not always true. The reason for this, that I say this, is that if you can't do it, 99% of the time, the reason why you can't do it is there's just no signal in the data. Okay? So it's not that you're just not smart enough, that humans somehow are not well equipped to handle the volume of data we have. The answer probably is there's just no signal in the data. And barring that, it's very hard to, if you don't move to sort of analyzing yourself, you don't have that as a recourse, it's very hard to know, is the problem really in the data itself? Is it somehow something the data just doesn't describe it? There's just not Twitter data that tells you what the stock market's going to do. Or in the case of our machines, maybe there's no signal that actually tells you whether it's going to fail or not. Is that the problem? Or is the problem just that you aren't getting kind of, if you aren't just processing the data in the right way, right? Is the machine learning algorithm just not smart enough somehow to figure out these correlations? The reality is we're really good at this kind of stuff as humans, especially if you can visualize it in the right way. If you can visualize these things, just like this, pretty much. Make plots like this, right? I mean, don't look at these signals in like a big Excel table. That wouldn't be very good, right? But if you can plot things, you can visualize them. We're really good at image recognition, things like this. We're much better, actually. I mean, probably image recognition, computers are getting pretty good these days too, but we're actually quite good at pattern recognition, right? So while we aren't perfect, and while there are going to be some sort of false negatives in this case, right? There are going to be cases where there's some task that is actually possible and we say it's not possible. In the vast majority of time, if you aren't to do this, you're going to end up trying to spend way too much time and effort looking at some impossible problem. So see if you can solve the problem, and I literally do mean that. I actually mean play a game. Actually create the interface, play the game, see what you can predict or not. And please do this on your projects too. I mean, I'm being quite literal here, and I've done this sort of literally in actual data science applications. And so this gives you a very good way of determining whether or not you actually have a chance at solving the problem or not. Okay? And so now if you've done this, there's one of two possibilities, right? Either you can solve the prediction problem, or you can't. Right? So either you're no better than random chance, or you are. If you are no better than random chance, then this is an impossible problem you found. And so you need to fix that somehow. And this is going to be step 2A in our little flow chart. If you can solve the problem, you've landed on a feasible problem. And this is one that you actually can, humans can do as well, or can solve. And so we want to now address the problem of, well, can we make an algorithm actually solve this too? Right? So this is going to be our little flow chart here. And I'm going to first go to step 2A, which addresses the problem of what happens if you cannot personally solve your prediction problem. So what do you do about impossible problems? Well, the goal obviously is going to be, at this point, to somehow change the problem to make it a feasible one. But the question, of course, is then how do we actually do that? Right? How do we actually go about making a possible problem out of all this? Okay, so you build, any questions so far? Can be at a very high level too. This is a very high level lecture, and frankly, if we don't have questions, we're going to finish early. Maybe that's a good thing, but for everyone here. But yeah. Yeah, sure. So actually, we'll show one next time in class. But literally, if you have like a classification task, just show the input in whatever form is easiest to actually analyze. Like if it's if it's an image you want to classify, then show the image and type in the classifier of what it is. Right. Select some options of what it could be, and then have a human click the right one. Right. Actually, go about this sort of process of trying to figure out, given all the exact same task that the computer has, try to go about solving this task yourself. So, an interface where you sort of see the example, maybe I see those signals there, and I click yes or no, is it going to fail or not, and then I, pop up, you're right or you're wrong, right? And do keep score, because it's, you will often, if you don't keep score, you will think that you can do better than chance, but you actually can't do better than chance. And you'll also waste a lot of time if you don't keep score. Yeah.
In the example that you just given for the signals, how do you know what the definition of failure is?
Oh, yeah. So in this case, it's actually quite well defined. A machine is going to either stop working or not. Say, and this is kind of a contrived example. I mean, it's not contrived. It's a toy, or again, the real problems here are not toy examples, but it's just an imaginary example so far. So a failure could be, at some turbine or something that's spinning just breaks down, right, and it can't spin anymore, so it can't produce any more energy, something like this, right? I'm assuming you know what failure means here. There can be different kinds of failures too, maybe in a more sophisticated example, but I'm just saying you know what failure is here. Your machine just stops working and it can't produce anything anymore. And that's actually a very concrete thing that you have, right? Because in historical data, you have these records of whether or not things actually failed, and you could use them to give very concrete labels to each part about whether or not it really failed in, say, some 60-day window after the current day. Right? And so that's going to be kind of the task we set up. And the question is, can you actually predict that? And the way to see if you can predict that is, plot the signals and determine if you can see anything in the data. And if you can't, it's going to be really hard for an algorithm to do so.
So I guess my question is are you just giving is my interface just what I'm seeing right now, the signal, and then from that to failure that is going up, failure that is going down?
Oh yeah, failure is not related to the signals here. Failure is a meta thing of, does this machine actually break or not? In addition to that, I have signals that monitor vibrations on the machine, or sound in the machine, or maybe it's usage or whatever. Those are features, and then the label that you have in the end is the actual failure or not. Yeah. There was one saw. Maybe not. Okay. Okay. So what do we do without impossible problems. And again, this is actually what typically happens. What usually happens is that on the first pass, you actually cannot solve your problem. Because you don't really know the problem very well. You kind of, hope that you can predict failure. But the reality is, if you could do it that easily, this would probably already be solved by someone, right? People are probably giving you problems as a data scientist that they can't solve with sort of other techniques. And so chances are your first pass at a problem will actually not be one that's solvable. And again, in my experience. So what do we do? Well, what you definitely don't do is you don't start running machine learning algorithms now. And throw bigger, badder, and more complex ones at your problem and see if that actually works. That will almost certainly fail. Instead, what you have to do is you have to change the problem. And these problems, remember, we're considering here sort of, and I sort of alluded to this whole time, but we're considering kind of these supervised learning problems, right? Where you have really two elements of the problem. You have the input and the output. The input in the case before were the actual signals of the machine, and the output was this binary flag of whether it failed or not. So in order to actually change this problem, you have to change one of two things, right? You have to change either the input or the output of this problem to make it possible. So let's talk first about changing the input, because it's it's one people are more familiar with, right? And this is, unfortunately, though, goes back a little bit to our old problem of the Twitter account you could find that would predict the stock market. Right, so you can always add more features, right? I could always record more signals from my machine. I could, integrate more additional data sources into my system somehow, in the hope of finding this one magical feature that makes my problem possible, right? Makes it a feasible problem. And there always is this hope that yes, we're gonna, the next thing we're gonna load, it's going to be this magic thing that maybe actually not by itself, but in conjunction with all our other data, somehow makes this problem really, really easy. The bad news is, though, there probably aren't these features. So adding more data is good. It's not probably going to hurt you, but there's a very good chance it actually won't help you either, right? There's a very good chance that whatever else you add to your data set, whatever other features you add, are of the same category that they, even with those new features, you won't be able to predict the actual label any better than you could before. So again, adding more data is good, but there's some cost to adding more data too, right? You have to go through the effort of loading the data source, standardizing it, integrating it, adding a feature to all your examples, et cetera. Especially if it's something like a sensor, this could be really hard because you have to actually install a new sensor and everything and hope that that's going to tell you the information about whether it's going to fail or not. So you can do this. I actually wouldn't recommend this as the first thing, but you can do this. But I would say give sort of two bits of advice here. The first is you should always do spot checks, and I mean visual spot checks, to see if this new feature you have to invest time in adding will actually give you any chance of predicting your target quantity. So do a quick check of this feature versus some summary statistic of this feature versus the failure of your machine, right? See if there's any hope that it has that correlation or not, right? Now, of course, it could be the fact that the feature by itself doesn't give any correlation, but combined with everything else, somehow magically combines to give you perfect prediction. Again, it probably won't happen. If your new feature is a good one, it probably will be somewhat correlated by itself, and possibly even more correlated with everything else, right? So you should be able to actually look at those time series in the same way you did before. Look at this new feature, and say yes, that one seems to go up or down before a failure happens. Say, okay. The second thing is to get advice from domain experts. All right. So this is actually something that should be actually very obvious, but I think also is not always done because people have the notion that somehow data scientists should be able to, overcome all that baggage that the domain experts have. They just couldn't realize the problem was just purely data-driven, and therefore easily amenable to these solutions. And so you don't listen to the mechanics to actually fix these things, right? That's a big problem, of course, right? Because the reality is people that do these things, that actually go out and fix the machines you're looking at, or that analyze whatever data that you analyze, maybe in more traditional ways, they're pretty good at what they do usually. They've been doing this for a very long time, and they have a very good sense of what they look at when they want to determine, say, if a machine's going to fail or not. So before you consider the whole universe of features, think about what features experts use that actually are experts in the domain at hand. What do they look at when they want to predict what's going to fail or not? Okay, so that's the only things I would say about getting more data. You have to balance these two things with how much time it will take you to add this new source and what your chances of success you think are. Because oftentimes, it's not that easy to add a new data source, and so before you do so, you have to figure out, is this really going to cause any benefit or not? Okay, but again, that's the more standard one. People sort of know that you can kind of add features and potentially get better performance on your problem. The one that's a little bit less commonly addressed is changing the output of your problem. And it's not addressed because it seems like cheating, right? We're just going to change the problem to make it easy. Let's just make them all zeros, and then it's easy problem then. We can definitely succeed at this one. Of course, you have to still preserve the character of the problem. So make the problem easier, but still preserve its character somehow, right? So how do you go about doing this, right? Because again, it seems like it is, if you don't use the ground truth data, what do you use for the output? And here's kind of the second big trick that I found is very useful. The first being, playing the game yourself. The second one being this one. So the very simple procedure is, instead of trying, a lot of tasks we want to predict the future, right? We want to predict what's going to happen tomorrow. And it's very hard to know if there's a signal in the future, on the past data that will really predict the future or not. So instead of trying to predict the future, try to predict what the experts would predict given that same information. All right? So what this means is, if you're doing a predictive maintenance task, instead of ask the question as your label, right? Instead of your label being, will this machine fail in 90 days? Make your label, would the people in charge of repairing these machines prioritize this machine or not, if they were looking at all the same signals you had? All right, so use, in other words, expert labels as the labels for your classification problem. Now, there's a lot of caveats here, because you have much more data problems then, right? You can't get that many labels. Maybe you can get a few here. You can't get too many. The other thing is, they may disagree oftentimes too. So you have to ask more than one person, right? Because if you ask two and they tell you very confidently, yes, this one's going to fail, this one's not going to fail, and they disagree on those things, then that's probably a good sign that this problem still may be impossible because there's no actual ground truth labeling. They're just making stuff up. It's probably good to check a little bit whether there's any correlation between their predictions and the reality, right? But there usually is, right? There usually aren't just, domain experts are not usually just making up things entirely. Even if they aren't perfect and can be improved upon, they still have a good sense of the basic elements of what makes something likely to fail versus not, for example. The other sort of warning, of course, is that if you just look at expert opinions, the danger there is that you never go beyond that, right? You never start to exploit more elements of the data that actually tell you the real failures above and beyond what someone might predict. But the way I think about it is that's sort of a version 2 feature, right? For version 1, when you're first addressing a problem, don't worry about exceeding human performance or finding the things that people are missing currently. If you are able, again, to replicate what domain experts can do, given a very long time to look at a single report, and you can mimic what they would prescribe in those conditions, that's a very valuable thing to do at a massive scale, at a scale that can be instantly kind of scaled up to as many machines or as big a size as you want. That's a very valuable thing to have. The real advantage about this approach, though, is that now, again, and again, assuming that two people are consistent in this case, that they aren't just making things up entirely, is that we already have an existence proof that this is now a feasible problem, right? Because our criteria for feasible problems were what would, can an expert predict this? But with the labels that an expert actually assigns to something about whether I would maintain it or not, we know for a fact that they already have that existence proof, so we're already guaranteed to be able to have a feasible problem in some sense or another. Okay, so this is a very, very nice proxy for don't predict the future, because we never know how much signal is in the current data to predict the future, but we know exactly how much signal is in the data to cause people to say yes or no when they look at something. All right? Now, again, you're going to have issues with sort of scale of data, all that kind of stuff. Maybe you don't want to just do this because you want to at some point integrate real failures. Yes, definitely. But for version 1, if it's possible, do this kind of thing. All right? At least as a way of sort of knowing whether or not you can really address this problem. Okay, so that's sort of the first thing that I mean by changing the output. The second thing I mean, this is actually a comment I made to a lot of people on their project proposals, is that it often also is worth reconsidering kind of what constitutes a good prediction. Right? And this is also important, especially when you have things like very highly imbalanced classes, very asymmetric costs to making different classifications. And the idea here is that you often want to move away from this notion of making good predictions to quantifying the uncertainty in the outcomes. Okay? So what I mean by that is the following. So let's take an example. And again, this sort of seems like a kind of a cop-out, because we're saying, okay, I'm not going to try to predict well anymore. I'm just going to try to say how uncertain I am when I get things wrong, right? So it feels kind of like a cop-out, but the reality is a lot of things in the world are just inherently stochastic. Machine failure, for example, is fundamentally many times truly a random quantity. There is nothing in path history that says whether this is going to fail or not. You can have a good machine and a bad machine that look exactly the same under the sensors that we actually have. And maybe even at any sensors we ever get to the level of the current time, they just are essentially the same. There's some micro fractures that we'll never see that change one, that make one different from the other one, right? But there's no signal in the data that actually quantifies that. All right. So the problem here is that it's going to be very hard for that reason, and many reasons. Maybe you just don't have many failures. Period. To accurately predict what's going to happen in the future. And so you want to what you really would like to do instead is just get some sense of the distribution of different possible outcomes. So for instance, if 10% of all machines fail in 90 days, say, so say of the current day it's a pretty large amount, maybe these are cheap machines or something like that, but maybe 10% of all machines fail within the next 90 days in your factory. So that means the nominal probability of a machine failing is 90%, or sorry, 10%. Of it living on past 90 days is 90%. And so if you're able to say that for a given machine, there's actually a 30% chance it's going to fail, and your probabilities are what are called well calibrated, so that when you make that prediction, if you make that prediction 100 times, then 30 actually will fail in the next 90 days. That still has incredible value, right? That still can actually mean the difference between maintaining that thing or not, and if the cost of maintenance is much, much less than the cost of it failing without maintaining it before, that can be a very, very big difference. Right? The point I want to make here is if you actually make a prediction about whether it's going to fail or not, you would still say, no, this is not going to fail. Right? You would still say, 70% chance, that's greater than 50. I would still predict, maybe everything, I would predict, no, it's not going to fail. But if you use a probabilistic classifier, right, if you actually look at quantifying the probability of your outputs rather than just making point predictions, you will get a sense of the distribution of possibilities you have, and that itself can be very valuable independent of your any kind of traditional accuracy you might have. Okay, so that's sort of what I mean by changing the problem. All right, you could add more inputs. change the output. That one typically works, or even sort of give up on good predictions and just focus on trying to quantify probabilities of different outcomes using a probabilistic classifier or something like this. Right? And what my experience has been is that after doing these things, you tend to have problems that can be now feasibly attacked. Right? So whereas before you may have a problem that you're getting just no better than random chance, when you do these things, I mean almost by definition with the previous one here, you will now have a problem that actually is feasible, and so we can now worry about actually applying algorithms and actually debugging these things. So we're going to step 2b, which is either if you got lucky and got there originally, or if you've now modified your problem to be feasible, what do you do with a feasible problem? Before I go though, any questions? Okay. So, good news now, right? Your prediction problem does seem to be feasible because you can solve it, or maybe you've given it to an expert and the expert can solve it. Right? So because of this, we believe the problem actually is solvable. We believe there is a signal in the data, and typically, for most current problems, I'll get to the exceptions a little bit later, but for most current problems, if you can solve it, that also means a machine learning algorithm will be able to solve it. So you can also address it with some sort of data science techniques. But what happens, maybe, is that you run your machine learning algorithm and find that it doesn't work. Or it performs much worse than you do. Right? So either it gets only slightly better than random chance, but not as well as you work, or maybe it doesn't work at all. It doesn't get any better than random chance. So again, you could try just throwing more algorithms at it, more data, more features, et cetera, and just hope that over time you're going to make this thing get better. This is a pretty bad strategy when it comes down to it. It's just not a very good strategy for actually making these things work in practice. So instead, what you want to do, and this is really where I would say, after we've settled on a problem, this is where almost all the time is actually spent in data science coding. It's not in sort of developing algorithms, certainly, and it's definitely not in writing the algorithms. It's actually in building diagnostics to check what the problems are in a current machine learning or data science pipeline. Right? And there are several good diagnostics that can kind of help you get at these things and help you identify what the problem is, which will then tell you, what's the most efficient and best next step you can take. All right, so let me give you a few of these things. This is actually my favorite one, which deals with the classic problem of overfitting or underfitting. Right, we actually already covered this a little bit. But the idea here is that one of my favorite plots to show to diagnose the performance of a machine learning algorithm is the performance of the loss as a function of the number of samples. Okay, so that's the number of data points we give to the classifier or give to the machine learning algorithm. In the training set, I mean. Okay, and what happens is that for both of these things, you plot both the training loss and the validation loss. All right, so both in your training set and your validation set, I'll plot what those are. And by looking at these figures, you can tell whether you're in what's called the high bias or the high variance regime, which we talked about a little bit before. I forget if I used those words or not, but I'll sort of describe it now if I didn't use those words before. So let's first consider this performance on the left here. So we have some loss, so lower here is better. And what's going to happen when you train your algorithm is that as you increase the number of samples, your training loss is going to increase, right? Because when you have very few examples, I can very easily fit them all with a classifier, right? And so I'm going to have very low loss on my training set. But of course, it's not going to generalize at all. So it's going to have very poor high loss on my validation set. As I increase the number of samples, these two lines are going to start converging. My training loss will start going up because I have to fit more and more data, so it's going to be harder and harder to fit it all. And my validation loss, should go down, right? And in the limit, the infinite limit, these two lines will always come together, right? Because in the limit of infinite data, training performance is always going to be equal to testing performance, but we'll never even come close to getting there with any reasonable set of data that we have. Just know that eventually those things should converge together. But two things can happen here. The first thing that can happen is that if we have our desired performance here, this is our, the level of loss we would like. They could both converge to a point which is where they're together and they are both higher than our desired performance. This is what's called the high bias regime, right? We have a high bias classifier. And the reason why is that, or the underfitting regime. And the reason why is that we can't even fit the training set here. So even for points for my data set where I'm giving the algorithm all the labels, it is still not able to fit this properly. In other words, this classifier we have, or algorithm we have, period, does not have the representational capacity to represent the function that we want to represent. Right? And this should never happen if you have a high enough capacity in a classifier. So clearly we just don't have enough capacity in our algorithm. Now, you can just look at the last point here, right? So what a lot of people do is they just float a plot what training areas and what testing areas, and if the gap's big, they say, oh, it's high bias. The gap's small, and they're both bad, they say high bias. If the gap's big, they say high variance. I like plotting this over the number of samples because it gives you a sense also of how your data, how your performance is evolving with respect to the number of samples too. So, if I double the number of samples, do I have a chance of doing a lot better? If I'm just here, for instance, right, it matters a lot how quickly these two things are converging together. So it'll give me a sense of whether I just need to add some more data, or if adding more data, is likely going to be kind of hopeless because they're kind of flatlining. We need to add a whole lot more data before these things start to actually converge. Anyway, this is why I like plotting it versus the number of samples. It's a very useful diagnostic. And by the way, to get these other points with lower samples, you just subsample your data. And this point here should be all your data, and these points should be a subsampled version of that. Okay, but this is the high bias regime, as I said. It's the time where you're underfitting, your classifier is not strong enough. And then contrast that with this case here, which is where your training set performance is very good, but your test set performance, validation set performance is not very good. In other words, it is not reaching the desired level. This is the classic sort of high variance or overfitting scenario, right? Where you do have a powerful enough classifier, but you aren't able to actually, get your test or validation performance, in line with it. Okay? And this is the overfitting or the high variance regime. Now, the point that I want to make now is that what you do, both these cases, I keep saying tests, the validation error is too high, right? But if you were to just look at that validation error, you would have no idea what to do next. Because what you do next, these different situations, is very different. So in this case here, you could do things like try a more complex classifier, right? Try a classifier with, say, try a neural network or gradient boosting instead of a linear classifier. If you're over here and you already have a linear classifier, then adding a neural network is not going to help things because you're already able to fit your data fine with a simple classifier. Adding a more complex classifier is not going to help anything. It's going to, overfit even more, perhaps. Okay? So what you do next is very different. On the other hand, if you're over here, then doing things like removing features, actually, adding more data, or all these things actually can be beneficial. So you actually want a simpler classifier here. And so you actually might want to do things like add regularization, or add more data, or try a simpler classifier, maybe remove features that you think are irrelevant. Right? That's what you want to do over there. Okay? So again, the point being is that you should not see your test performance being bad and just go ahead and try something new, because if I here and I spend a month collecting more data, it's not going to help me at all over here, right? And so I've spent all this time collecting more data without any actual reason for doing so. Similarly, if I'm over here and I try 100 different classifiers, all with different hyperparameters, much more complex ones, it probably won't help there. What I need is actually a simpler classifier over here. Okay, so this is by far, I should say, the most common diagnostic to run too. This is the one you should be running. If you want to debug the performance of machine learning algorithm, you should definitely be running this one. But there are a few more that come up as well. And so I want to highlight a few other possibilities at least. They're going to be less common, but they are things you should sort of be aware of. So one of them deals with optimization performance. This is especially a problem with things like large models like deep networks, right? Where actually the actual optimization performance of these things, they take a while to train, and there is some sort of there's some degree of sophistication in the actual training procedures themselves. So a lot of machine learning algorithms, as we know, are iterative algorithms. They work by trying to minimize their loss, but they like running gradient descent, and so they keep doing this iteratively. And there's a chance that whenever your classifier returned, it just wasn't quite done yet, right? So you're optimizing things. Here's your, say, optimization iterations, and here's your loss function. And had you just kept running a little bit longer, you would get perfectly good performance after some time. Less common, certainly. What's much more common is you have something like this in the high bias case or this in the high variance case. But it's good to actually plot this and ensure you are actually seeing this. The other possibility, by the way, is that actually you've optimized for too long. So this is something called early stopping in a lot of iterative optimization techniques. And if you actually, there are cases in things like deep networks where, especially with non-convex and sort of things that have local optima, you actually, after a time, your training set loss might keep going down, but your validation loss can go up after more training. And you want to stop kind of at the right time where it's the lowest that it can be. So plotting optimization performance is a good way of sort of looking at the details of how your algorithm is actually working and sort of what might be going on underneath the hood. And the last point I want to make is considering the loss that your algorithm is optimizing versus the actual task error you care about. This is also a subtle one. This one actually is fairly common. But the idea here is that every algorithm we've talked about minimizes some loss function. Right? That's how they work. That's how we define them. They have a hypothesis class, a loss function, and an optimization procedure. So they work by minimizing loss. Via, say, optimization iterations, but this could actually be other things too. Right? This could actually be anything on the x-axis here. And so if you look at sort of added complexity of the classifier, maybe added optimization iterations, what you'll find is that over time, what these things are doing is they are minimizing loss. And so they're getting better and better at minimizing this loss function. But oftentimes, what you actually care about is something different. What you actually care about is not just this loss function, and I'm showing it here going up only in validation, but it could also actually even go up in training too. What you care about is not this loss function. What you care about oftentimes is some very complex thing, like when I use this prediction to recommend things to people, do they actually buy more stuff or not? Or do they understand this stuff better or not, right? It's a very sort of abstract notion. Or maybe, for the maintenance case, if I recommend maintenance based upon this prioritized list, do I have less total cost of operations than if I don't do this, right? So it's a very complex, and there can be all sorts of sort of added complexities there about how many people you have to maintain things, this kind of stuff, right? What the cost of maintenance is, what the cost of a failure is, all these kind of things. So the point here is that, and especially also in cases when you have, for example, imbalanced data sets, when you have one classification example is very different from other ones, and so you have to sort of figure out how to balance those two. This can be a big difference. And so remember that machine learning algorithms are not optimizing typically what you actually care about. They are optimizing some very simple loss function. And you should see as much as you can, not just the performance of that loss function, but the actual performance on task error of these things. So actually compute as much as you can. You can't do it always fully, but as much as you can, compute your actual task error of the problem and see how well it actually performs on that real thing you care about. Now, there are a few more, but these are sort of three common examples. I mean, the first one is by far the most common, but these are three kind of common diagnostics you can run. And the reality is most of the time that I spend when I'm coding on a data science problem is not any algorithmic development. It's just coding diagnostics like this to check why is my performance not at the level that I think it should be. Now, the very last possibility that there is, though, So remember, this is in the scenario of you can solve your problem, but the machine learning algorithm cannot seem to be able to. So you've done everything you possibly can here. You have a problem that you really can solve. You know exactly what's going to fail or not. You can look at these signals. You can determine exactly what's going to happen. I can look at this data and figure out what the answer should be, but the algorithm cannot do it. So the last thing you can do is you can go back to school and get a PhD. Not because you'd be any smarter then, but because this is the kind of thing we study as researchers, right? You may have genuinely stumbled upon a problem which we sort of informally call AI hard, right? Which is somehow your problem that you found is easy for humans and really, really hard for computers to do. So things like, say, natural language processing, understanding. This is exactly those kind of problems, right? So if your problem involves, for example, free text and a conversation and analyzing a conversation and figure out what's happening, that could actually be very hard for a computer to do, even though you can do it, right? And in some sense, these are actually the best problems that there are. They're the most interesting problems for us as researchers. But you don't want, assuming you don't want to go back. I guess some people here maybe already are getting their PhDs. So don't. In that case, you're already, you've already done this, so you're already down that path. But assuming you don't want to do that, and invest, 5 years of your life on solving natural language processing, and maybe your whole life, if you go down the even worse path. These are really interesting questions, but assuming you don't want to solve these in the course of, a 3-month data science engagement, which is probably going to be the case for most jobs you're in data science. You want to go back and adjust the problem some more. So maybe you really have some of the problem that is possible for you but not possible for computers, and currently not possible for the very, very best machine learning algorithms to do. That's fantastic. Hand it off to the folks that really love finding these things, because we actually do love finding them. They're getting harder and harder to find these days. Things with computers are really at least easy tasks, one-off tasks you can have described very succinctly, but which they're much better at. Natural language processing, obviously, being an example, is still very much there. But don't try to solve it in the course of your data science problem. Try to look at the problem in some other way that maybe makes it easier to solve than this. Okay, any questions now? So we're almost done. Everyone go off a little early. But there is one other pitfall I want to mention, which is actually probably even more common than all these things. And that is the problem of impossibly good performance. This is the other big thing to watch out for. So here's the other possibility that can happen, is that you run your machine learning algorithm, and right off the bat, it gets kind of amazing performance. Right? You're going to revolutionize this field. You're going to sort of make everything different. No one's going to ever use anything but your technique to analyze whether things are going to fail or not in factories, right? So the thing I'll say here is that you should be really skeptical if this happens. Unless your problem is just so obviously easy that you already know it would be solvable and you just didn't want to go through the effort of doing it yourself, so you just let a machine learning do it, fine. Then okay. But if your problem is not obvious to you, still go through the effort of solving it manually. If you can solve it manually now, then you have maybe some sense, okay, this is a possible problem. I can solve it. I couldn't quite say how I solved it, but I can believe a computer can do it. But if you can't solve it manually, be very, very skeptical. Move from skepticism to extremely skeptical. And the reason for this is it's very easy to cheat when it comes to data science. So it's very easy to accidentally include some feature or some bit of information that gives away the answer. That basically says, okay, for this, include a feature that is essentially a transformed version of the class you're trying to predict. Right? And this happens all the time. And it's not actually ever malicious, right? No one ever wants to do this. People know, they're not trying to get better numbers, and so including the class label as one of their features. What typically happens is that data in its native form that you're going to be loading in will somehow leak information that you don't want it to. So one of the things I've seen, I actually saw this in an example of predictive maintenance tasks. So what companies would do is after something had failed, they would go back some time before the failure, and they would say, well, look, I know the data was unreliable in this time because it's about to fail, so I'm just going to zero it all out because it doesn't really matter. So our classifier would very happily pick up on this fact because they didn't want to include it in their averages or whatever, so they would fill it in with some nominal value. So our classifier very happily then saw this value that they filled it in with and said, aha, it's about to fail, and we were always right? So we were getting 100% accuracy, doing amazingly well, and of course it was completely bogus because it wasn't actually picking up on anything you would have at the time when something was actually going to fail. So this happens all the time, that there is some little bit of information that is leaked into your training set or into your features that kind of gives away the answer that you don't actually have when you run these things in real time. So the way you kind of get around this is that you should do things like, well, first of all, try to solve it yourself. And if you can't do that, then that's a good reason to believe something is skeptical. And then next, run something like an interpretable classifier. So run that decision tree, a very simple machine learning algorithm to identify, what are the things it's picking up on, the sort of key on it being, really easy to solve. And if you see a clause that says, if this data point is equal to 0, then failure equals 100%. Say, well, I wonder what this data point is. Look at it, what it is, and then make sure that maybe there really is, again, somewhere buried in there, a magic feature that tells you what's going to happen. But these are ways you can kind of go after that and really find these things. So actually running, again, even if you don't believe in classifier interpretability for its own sake, interpretable classifiers are very, very good for debugging data sets and figuring out what are the oddities of a data set that make this too easy or too hard. Because this does happen all the time, and announcing success prematurely will feel very, very bad if you then try to deploy your thing and realize it doesn't work any of the time. Okay, so that's actually all for today. But to summarize, there's really 4 possibilities when you talk about machine learning. Either you predict well or not, and then the machine learning algorithm can predict well or not. If you both predict well and ML predicts well, that's actually where we want to be. We want to be in a situation where you can solve the problem, maybe not immediately, but you can solve it with some challenges, and so can machine learning. That's the good place to be. You predict well and ML predicts poorly. That's a feasible problem that you can now start to apply those techniques of looking at diagnostics for what's going wrong with your machine learning algorithm. If you predict poorly and the machine learning predicts well, be very skeptical that you aren't cheating somehow. And if you both predict poorly, you've stumbled upon an impossible problem, and so you want to actually change it to make it possible. And I really have found keeping this kind of rubric in mind, it's not perfect, but keeping this rubric in mind when you're looking at data science problems is extremely helpful for sort of getting yourself out of these ruts when you just don't know what you should actually be looking at next and why your problem does not seem to be amenable to the kind of analysis you want to do. This kind of analysis and this kind of mindset can be very helpful in debugging that. And in fact, next lecture, could have started this time, but I guess I didn't quite get everything ready in time. Next lecture, we're actually going to go through an example. I'm going to walk us through a data science example. It's going to be a simple one, but I will sort of walk us through and kind of touch on many of these points and touch on how I debug some of the elements of these systems and of these data science pipelines. So see you all next time.